This is the first in a series of videos about acid-base titrations at the end of the acid-base chapter. We're going to talk about how to determine whether the acid or the base is the titrant in a titration curve, how to look at the curve shape to indicate whether a strong acid or strong base is being used or whether a weak acid or weak base is being used. And then we'll look at how to calculate the pH at various points in the titration to indicate the varying levels of completion. So you should have a little bit of knowledge about what a titration is already. This should look like a familiar setup. We usually have a burette, and that burette is full of liquid that we know a lot of information about. So we call this liquid the titrant. And the titrant has a known concentration and a known volume. And then we drop that liquid in the burette into some sort of a flask or a beaker. And that liquid is called the analyte. And the analyte has an unknown concentration. We're trying to solve for the concentration of this part. So one new thing that we add when we're doing an acid or base titration is we add a pH meter. A pH meter is an easy way to monitor how close to the equivalence point your titration is, whether it's more acidic or whether it's more basic. And so we can make what's called a titration curve to reflect this data and to show how far our progress is in a titration. So as we add a little bit more and a little bit more titrant, we can put that volume on our x-axis. We can call that the titrant added. And we usually put it in milliliters. And then as we add the titrant, the pH of the system is going to change. So we'll put the pH on our y-axis. The amount of analyte and the concentration doesn't change, so we don't need to plot this number. So this is what our plot's going to look like, and I'll go ahead and add my units to my other one here. If you'd like a copy of these blank pages to draw on, you can find it posted on Moodle. Otherwise, you can draw them yourself, as I'm going to do. And I used blank printer paper today instead of lined paper so that I can really clearly see what these pictures look like. So I'm going to draw an example of what some titration curves look like, and we're going to talk about the anatomy of a titration curve. So here's an example of one. And here is another one. So they have sort of a slightly increasing piece, a very steep increasing part, and then a slightly increasing piece again. So there's a couple of pretty obvious sections of this. The first is that there's sort of two halves. There's a left half where the pH is really low, and there's a right half where the pH is really high. So we can sort of draw a dashed line here to divide those two halves. So we'll label this the low pH side, and this half is the high pH side. And since this is the end of the acid and base chapter, we know what the pH value indicates about the acid level. As we're adding the titrant to the analyte, one of these pieces is going to be an acid, and one of them is going to be a base. And so at any point on the left or right half of the titration, you're always going to have more of the acid, or you're going to have more of the base. And we can tell which we have more of based on the pH. So if we have a low pH, that means we're going to have excess of the acid. We have more acid than base, we're going to have an acidic solution, it's going to have a low pH. And the opposite is true over here. If we have a high pH, that means we have excess base. We have more base than acid, we have a pH greater than 7. So we can identify the left half and the right half, and this point in the middle. This is the steepest part of the curve. There's a really tall, steep vertical section, and we call this the equivalence point. This should be something you're familiar with from your previous titrations. The equivalence point is where the moles of the titrant are equal to the moles of the analyte, and that is also true here. And so we can make an observation about what sort of compound is in the burette acting as our titrant based on the shape of this curve. So we know that the titrant amount is on the x-axis, and it goes from very low amounts to very high amounts. And so we can look at our acid and our base and look at which one matches that axis. So this acid goes from high to low, and this base goes from low to high because it has the highest amount on the right side, just like this axis. So that means that our titrant is going to be a base for this picture. So the base would be the titrant in the burette, and the acid would be the analyte in the flask. Okay, and let's look at our other curve just to make sure we see what the other situation looks like. So this shape, it's the opposite direction of an S. We can divide the left half and the right half from a dotted line. We see the equivalence point here in the middle. And we can see that this side is a high pH side, meaning that there's excess base at the beginning of the titration. And over here on the right, we have a very low pH on this half, telling us that there is excess acid at the end of the titration. And if the end of the titration has excess acid, just like how it has excess titrant, that means that the titrant has to be a strong acid. Okay, so this is what a base titrant versus an acid titrant looks like. So now that we've looked at titrating with an acid and titrating with a base, we need to talk about strong versus weak acids and strong versus weak bases. We can titrate strong with weak, or we can titrate strong with strong. And even if your axes aren't properly labeled, you can identify what was used in the reaction based on the shape of the curve. So we're going to draw a few different shapes and talk about how we can tell which pieces are used. And this page is also posted on Moodle if you'd like to use it. Okay, so we're going to draw a couple of different curve shapes here, and then we'll talk about how they're different. So the first two, this first one is going to look like our first one on the last page, with flat and steep and flat. And this next one is going to look a little different. It's going to start a little bit higher. It's going to have a flat section here on the left, and then a steep section, and then it's going to resemble the other one. And we'll label our axes, pH on the Y, titrant volume on the X. Okay, and we can use our skills that we used on the previous page to make our same preliminary observations. So we can see that this left half is the excess acid half because the pH is low. We can see that the right half is excess base half because the pH is high. And the label on the right side matches the titrant. So if we have excess base on the right, we're going to have base as our titrant. And it's the same for this picture over here. Even though it looks a little bit different, we still have lower pH and excess acid on the left, higher pH and excess base on the right. And excess base on the right side means the titrant is going to be a base. And we can mark the equivalence point on these as well, on their steepest vertical section. Okay, so those are what makes the graph the same. Their left and right halves and their equivalence point. So now let's look at what makes these curves different. So one thing that makes them different is the pH at the very beginning and the very end of the titration. So at the very beginning in the excess acid region, we can see that that pH is very low. I didn't put numbers on the axis, but you can see it's much lower than the one in the other picture. So we're going to say this pH is between 0 and 2. And if an acid has a pH between 0 and 2, we know that's going to be a strong acid. Okay, over here in the left picture, the initial pH is a little bit closer to the middle than it was in the last one. We're going to say it's still on the acidic side, so it's still less than 7, but it's greater than 2. It's not all the way at the bottom of the figure, and an acid with a pH between 2 and 7 is a weak acid. If we look at the right side, we can see that these two look pretty much the same. The pH value here is all the way at the top, its highest possible level, between 12 and 14. And a base that has a pH between 12 and 14 is a strong base. And this picture on the other picture looks the same. This pH is also between 12 and 14. So it's also going to be a strong base. And it makes sense because we said that both of these pictures were titrated with base, and we always titrate with a strong piece. We could titrate with a weak piece, but the titration would take a really long time and a large volume of material. It's more efficient to titrate with something strong. So the right half of these two graphs matches because it represents when we have excess titrant, excess strong base. Let's see, what else can we find that looks different about these two pictures? So another thing that looks different on the left half is the shape of the curve, right? On the strong picture, we can label them. So this one's going to be strong acid, strong base. And this one is going to be weak acid, strong base. We like to name them from left to right, the left region and then the right region. So looking at the curvature of the strong acid, strong base curve, this curve is inflected up and it slowly increases up until it hits the equivalence point, whereas on this side, it increases and then there's a flat region in the middle before it starts to increase. And so this flat region is where buffering action is happening, and the very flattest part, halfway to the equivalence point, has a special name in a weak acid curve, and it's called the midpoint. And we give a special name to that because there's an easy way to find the pH at that point. The pH is going to be equal to the pKa of the weak acid. So that one is an easy one to solve for mathematically. So the curvature of that first part looks different. The curvature of the second part looks basically the same. The pH is a little bit different in the first part, and the pH is a little bit is the same for the second part. And the final thing we should look at is the equivalence point. So it may not be super obvious from the picture, but I hope you can tell that the pH for the equivalence point is a little bit lower than the pH for the equivalence point for the weak acid. So whenever you have a strong acid and a strong base, your pH is going to be equal to 7 at the equivalence point. That is always going to be true. And in this case, it's not going to be equal to 7, and we can guess whether it's going to be higher or lower based on the strong piece. So the pH of the equivalence point is going to be closer to the pH of the strong piece. And since our strong piece is a base, the pH here is going to be slightly greater than 7. It's going to be slightly greater and closer to that strong piece. Okay, so our three similar parts, the acid on the left, the base on the right, and the equivalence point in the middle, those were the same. The differences were the pH on the weak side, the curvature on the weak side, and the value for the pH at the equivalence point were different. And for the sake of completeness, let's go ahead and draw the other two most commonly encountered curves. So this one is going to match the one on the bottom of the first page. And here is a slightly different one. We'll start a little bit lower. We'll have a slight steep region and then a flat region and then a steep region matching the left side. I realize that these pictures are not as good when I draw them or when you draw them, But drawing the pictures by hand helps you to figure out which parts of the picture are important. And it helps you to understand it better when you draw it yourself. Okay, so looking at this, I can separate the left half from the right half. I can see that the left half has a high pH, so that's going to be my excess base side. And the right half has a low pH, that's going to be my excess acid side. So if I have excess acid on the right, that means my titrant is going to be an acid. And it'll be the same over here. Okay, and we can mark the equivalence point in the middle. We'll just abbreviate it because it's starting to get too big for the picture. There we go. So let's start with the equivalence point since we're already there. This is a strong acid, strong base titration. Oh, I guess we don't know that yet. I guess we should figure that out before we mark the equivalence point. So if we look at the pH at the very beginning in the excess base region, there's a high pH at that end of the picture, and a high pH indicates a strong base. Over here in the second picture, the pH is a little bit lower. We could say that it's somewhere between 7 and 12. So it's not going to be high enough to be a strong base, but it's still greater than 7. So it's going to be a weak base. And then over here on the right side, this pH is going to be very low, somewhere between 0 and 2. So that means this is going to be a strong acid. And the pH on this picture looks very much the same. It's also very low, between 0 and 2. So it's also going to be a strong acid. So that means the titrant that we're using is a strong acid. Almost all the time when you do a titration, you will have one strong piece at least. So that means that this one is going to be called strong base, strong acid titration. And this one is going to be called weak base, strong acid titration. Okay, so now let's go back to our equivalence point. Since we know this one is a strong, strong titration, its equivalent point pH is always going to be equal to 7. And over here, this is a different situation. This time we have weak base, strong acid. So we know that the pH at the equivalence point is not going to be equal to 7. It's going to be a little bit closer to the strong part. So it's going to be on the smaller side of 7. So it's going to be a little bit less than 7. Again, it's kind of like taking the average of these values. It's like averaging 12 and 0. You would end up with a number slightly below 7. And if you averaged 14 and 0, you would end up with 7 on this picture. So this has been the anatomy of different types of phase diagrams. You should be able to identify from a picture what the titrant is and whether the titrant is strong or weak, and whether the analyte is strong or weak. In the next video, we will talk about how to calculate the pH at different points in the titration curve.